Yeah, and thank you for the invitation. It's of course fantastic to be here and talk about this very nice topic on Feynman integrals and their geometric structure. And yeah, I hope it's going to be interesting for everyone. And as before, if there are any questions, feel free to ask. Let's keep this as interactive as possible. Yeah, so, and also if I write too small or anything like this.
Are those your notes, Nishi?
Yeah.
Awesome.
Why not? So, I want to talk about, or I want to give some motivation. And this is the amplitude school. So the motivation are obviously amplitudes. And I have this kind of cartoonish idea of amplitudes. So for me, an amplitude is just a function or a number, and you can write it. So this is the defining property. You can write it as a sum over graphs. We sum over some graphs, and the graphs have a certain restriction. So they say have L loops. And they also have other restrictions. So we want to have like certain decorations on the graphs, maybe some colors or tensor structure or anything like this. So we are including this implicitly in the sum. And for each graph, we have to compute something. And we also have this symmetry factor, which is not so important. And this thing that we need to compute is, of course, the Feynman integral. And yeah, these Feynman integrals are the topic of these lectures. No, I lost one blackboard. Oh, no. So the application of this is, of course, as we already heard today, are collider experiments. So these amplitudes or correlation functions, so they're closely related to correlation functions. They apply applications to collider physics. And if you have been here last week, you heard like many talks on applications also on classical physics, mainly gravity. So you can use the same tool for many different things. But what I want to emphasize here is that this cartoon formula is unfortunately the only way to compute many quantities in quantum field theory or in applications of quantum field theory. So this is a problem because this formula has a very big caveat. And the caveat is that there are many of these graphs. So, so the big problem of this perturbative approach is that there are sort of order L plus m factorially many Feynman diagrams or Feynman graphs. So this formula, it requires us to sum over something of the order of factorial, where m is the number of external legs. So here this is the number of legs, and L is the number of loops. And so there's a big combinatorial explosion hiding here. And it's an open problem on how to avoid this combinatorial explosion. And one thing that I would like to invite you on, or why I think this is an interesting topic to think about these Feynman integrals, is like taking the bull by the horn and just like tackling these Feynman integrals directly and trying to avoid this combinatorial explosion by studying these Feynman integrals very deeply. So this is good news for all the PhD students, for instance. So there's like many open problems in this business, and one of them is to avoid this combinatorial explosion. So yeah. There's also other motivations that I want to mention. So there's like bonus motivation. And this is more for the mathematicians. So who identifies as a mathematician in the audience? Ah, okay. Yeah, a couple of them. Not so many. Actually, there are also like non-mathematical interesting motivations, but so you can say, okay, we are only interested in these amplitudes or these kind of perturbative problems in classical physics. But I'd like to convince you that also looking into the Feynman diagrams themselves is interesting, even though we have this explosion problem over there. So here we are just sort of thinking about these individual Feynman integrals, and here's a cartoon of them. So usually they are written in this loop momentum form where we integrate over some loop momenta, and we have here in the integrand we have these propagators that are called dE, and these integrals, they in mathematics they appear as modular space invariants. So you can study invariance of interesting spaces, spaces or objects. Sure. Yeah. That's a mathematical application. More physicsy are also interesting. The application to cosmology, plus also in collider physics, we need to tackle different integrals that are also closely related to these here, which are called phase-space integrals. So these go beyond the typical Feynman integrals and beyond the amplitudes. But these are also very relevant. And they are kind of related to these, and they also make this very interesting. And besides this is also a very interesting mathematical theory that's hiding behind the Feynman integrals. Right, so some natural questions. that I'd like to tackle, or that I'd like to discuss. First of all, so yeah, what would you like to ask about these integrals or these sums? And one of the most common question is what is the analytic answer to such an integral? So we want to write down some formula for a given integral. And the problem with this question is that it's a bit vague and not really well defined. And I want to make it a bit more concrete. So the question can be reformulated like, what is the value for concrete external input? And how to compute this value as fast as possible. So how to compute it. So this kind of question is usually implicit in these kind of questions where you're supposed to write down some analytic answer for an integral. Yes, please.
Is there a reason before we start thinking about physical principles to just expect analyticity? Is that kind of, at least from previous
analytic expression? Yeah, so maybe replace analytic with closed form, or I don't know. This should be in quotes. So some kind of expression for the integral. So it's not really like a well-defined question. So this is exactly the point. So these kind of questions are asked very often, and they are of course also very relevant. But I think it's worth to think a bit about their meaning. And especially, it's helpful to be a bit more down to earth and ask a bit more mathematical, precise questions, maybe. So for a mathematician, this is more down to earth. For a physicist, it's maybe like a bit highbrow to ask, is it finite? That's already like a good question for Feynman integrals because it's non-trivial. It's highly non-trivial, actually. So this question on these kind of integrals is not, it's surprisingly hard to answer this question for general Feynman integrals. And then it's very interesting for various physical applications to study these divergences of these integrals. So there's like question 3a. So if it's not finite, where does the divergence come from? And how bad it is. Then we can also ask what's the behavior in a specific limit. There's also like a mathematically nice question, which is very relevant for this invariant computation, which is it non-zero? It's perhaps not so relevant for physics. And then it's also a big business to ask about the relations between Feynman integrals. So it turns out that many linear combinations of Feynman integrals are zero. And in mathematics, this is always a very interesting phenomenon. So we like to know these kind of relations and study them. And these relations. They are both interesting mathematically, and they are also very interesting for applications because we need the relations to simplify the computations. Yep. So about the first question, so what's the closed form expression? I want to write down an example. So I'll show you one explicit Feynman diagram and its evaluation, just that you saw it. So what does the closed form expression actually mean? So we can write down, so here's an example of a Feynman graph with external momentum P1, P2, and P3. And we say it's the propagators are all scalar and massless. And I think that everybody in this room can probably just write down the Feynman integral for this graph. Let's say we are in Euclidean space. So this is just going to be a integral over, so we are in four-dimensional Euclidean space. It's over an integral over R4. And we integrate some loop momentum. So the loop runs around the circle here. And in the denominator, we have k square, k plus p1 square, and k plus p1 plus p2 square. And maybe we have some pi square normalization factor. And you can check, or you can also just believe me, that this is a perfectly finite integral, which we can just compute. But there's also an analytic answer for this integral. So we have an analytic answer, or closed form answer. Which looks as follows. Let's say this is like star. Oops. So it's 4i times something which is called d of z and z bar over z minus z bar. So these are just symbols, but they have a meaning. So we choose z and z bar. So z is like a complex number, and we choose it such that z times z bar is equal to p3 minus p1 squared over p2 minus p1 squared. And so this is a quadratic equation. So is an equation in z and z bar, so we need another equation. And this is the following, that we have another expression for minus z, 1 minus z times 1 minus z bar. And this is supposed to be p3 minus p2 square over p1 minus p2. And then there's an expression for this d function. It's supposed to be the imaginary part of Li2 of z plus a log of 1 minus z log of absolute z, parenthesis closed. And then this Li2 has also various formulas for it, but one of them is just as a power series. So it's the dialog. So we can write it as an infinite sum over n, and we sum z to the power of n over n squared. So this is like, this counts like as a closed form expression for this integral, or what people would consider to be like a closed form expression of this integral. But now it already took me like significantly longer to write that down than to just write down the integral. So you might ask, what's the purpose of this closed form expression here in the first place? And yeah, so I don't know, maybe can try to make this a bit interactive. So what's the difference? So what's better? Why is the closed form expression better than the integral? Someone has any? Yep.
Easier to evaluate numerically.
Yes, exactly. This is the difference. So here, this is like conceptually simpler, I would say. So we can just write down this expression very easily. Here we have an algorithm that is encoded in this expression. And with this algorithm, we can evaluate the Feynman integral very quickly. And the whole business, say, of dealing with these Feynman integrals from this application-focused point of view is to, or not the whole business, but large chunks of this business, is to find good ways to evaluate these integrals fast. And here, even though we have a perfectly finite integral, there's actually no like really fast way to evaluate this one. But here we have a fast way, yes?
What's the dependence on Z bar in D?
Z bar in D. Yeah, so this is absolute of Z, and we take the imaginary part.
And the question was, where's the dependence on Z bar?
Right. It's like Jeopardy. This is the absolute value here, right? And we take the imaginary part. So the question was where the absolute value goes, right? Okay. Yeah, so what's also interesting here is that these kind of very fascinating functions appear, these dialogues and their relatives. And you can find like analytic expressions for lots of Feynman graphs that involve like more complicated flavors of these kind of functions, and huge amounts of intellectual energy actually go into like evaluating these integrals in terms of these functions. And there's also fascinating mathematics involved in evaluating these functions and studying their relations and everything. Yeah, so I'm not going to talk about this in these lectures. I'm just going to mention that it's a very fascinating story. One problem there is that we know that these kind of polylogs and their relatives, they are known to be not enough for all Feynman integrals. So we will find Feynman integrals where these polylogs are not sufficient, and we can then augment these polylogs by so-called elliptic polylogs and then go even further and so on. But in a way, this is an uphill battle because there's going to be like more and more complicated functions that appear the further we go up with the loop order and the complexity of these integrals. And yeah, so the issue is that the simplicity of these kind of integrals and their beauty from the perspective of the Feynman integrals is maybe a bit of an accident. So there's like more and more complicated functions popping up if we try to write down closed form expressions for them. Yes?
I wanted to know, with your z bar, the expression at the end, is it 3 and 2? Because in the first case, you wrote 3, 1, P3, P1. And in the other case, it's that the numerator became 3 and 2. The numerator, P3 P2.
Yes.
Is it a 2? Is it P2?
Yes, this is a 2.
And this is P1 at the other end.
Yes.
Okay.
Yeah.
And then the next question I wanted to ask, the integral, Feynman integral you wrote previously has some structure that looks like the Igusa integral functions. Does it have any relationship?
The Igusa integral, I don't know. I don't know which kind of function that is actually. Yeah, so why are they interested in like these fast algorithms to evaluate these integrals? We are interested in them because for the applications, we need to crank out a lot of numbers for these Feynman integrals. For the collider experiments, we need to crank out these numbers to compare the theory predictions of these amplitudes with the measurements, say at the LHC. And we also need to compute the values of these amplitudes for the phenomenology of the gravitational waves, for instance. And this is, so I mean, just to mention it, so there's, in these kind of computations, especially on the phase-space side, there's going so much computational energy in there. So 10 million CPU hours are not a unseen quantity for the computer time that it takes to evaluate these kind of integrals. So if you want to do something good for the environment, this is also a very good thing to improve the evaluation of these integrals. So yeah, so doing something smart with the mathematics can really have a big impact because these integrals are evaluated so often. Yeah, so in these lectures, I'm going to go through like some math structure.
Sorry to interrupt. Why isn't the 3-point scalar amplitude completely fixed by symmetry?
The 3-point scalar amplitude
Massless, yeah, also.
completely fixed by symmetry.
Yeah.
Uh,
Isn't it just a number?
it's not a conformal amplitude. Yeah, we are not in, there's no conformal symmetry here. This is not n equals 4. It's like other, this is more, still more down to a less symmetric quantum field theory.
Okay.
That's for the massless and non-shell.
Yeah,
Yeah.
right, yes. So this is off shell, right? So this P square, P1, so one of them has to be massive, at least
I
one
see.
of them.
Okay, thanks.
So you don't have, you cannot scatter like 3 light-like things against each other, right? So this is, yeah. So I said massless here, but I only meant massless for these internal propagators. So you have to have some mass going in here. That's true. Sorry about that. Yeah, so I will go through the mathematical structure of these Feynman integrals and focus on the geometry aspect to it, and in particular on this tropical geometry aspect. Yeah. So to do that, I'm going to start with the parametric representation. To make some space. Oof. Let me get this up somehow again here. Not so good. Okay, so these integrals, they are not so nice from a mathematical standpoint. In particular, these integrals, this general form where we also want to allow like a arbitrary d-dimensional space-time dimension where d might also be like a real number or complex number, are not so handy, both not for numerical evaluation or mathematical analysis. So it's very convenient to go to a different representation. And for the rest of this lecture, I'm going to explain how this works. So we want to go to a parametric representation. So here's a general form of these Feynman integrals, which is convenient to perform this change of coordinates, let's say, but it's not really a change of coordinates. So we have one d-dimensional integral for each edge of some graph. And somehow normalized. So the parametric representation is always based on some Feynman graph. And we think of the Feynman graph as given as a pair of some edges and some vertices. For each edge, we take a d-dimensional measure over a d-dimensional space. And we also take a propagator, which is usually, at least in Minkowski space, written with this causal I epsilon prescription. And then it's convenient to also give these propagators an arbitrary power, an edge weight called nu e. And then for the vertices, so for each vertex, we also have a product. And we want to actually leave out one arbitrary vertex. And it will be apparent why we do that. So for each vertex, we also have a normalization factor. And then we have a delta function, which ensures momentum conservation at the respective vertex. The reason why we take out a specific vertex is that we are not interested in overall momentum conservation. So this can always leave one out because all the other this extra delta function will just ensure that the overall momenta are fixed. And this epsilon IV is a certain matrix that comes from the combinatorics of the graph. And in fact, this epsilon matrix here is the only point of input where the combinatorics of the graph actually play a role. So just to explain this in more detail. So here we integrate over space-time. And we have the space-time is d-dimensional, capital D-dimensional. And this stuff here ensures momentum conservation. And this epsilon is for causality. And these nu e are some at rates. And what is implicit there is that we choose some space-time signature. And the space-time signature only comes in this QE square term up there. And this epsilon VE, epsilon EV, is the graph's incidence matrix. So this is where the combinatorics actually come into play. And to compute it, we need an arbitrary orientation on the graph's edges.
Like, can you do
Yes.
the retarded contour exactly, and I can still replicate the exact same formula?
Yeah, it's kind of interesting that actually, so the question is if you can take different versions of the Feynman propagator with different boundary conditions. And the answer is, as will become apparent later, that there are actually only two choices where this kind of works quite well with respect to this parametric representation, namely this one with the I epsilon and the completely Euclidean choice. So any advanced or purely retarded propagators are not allowed, at least in the specific representation that I'm going to derive from this. So, but this is kind of interesting, and I invite you to look into the point to look at the or to study the point where this actually fails eventually. And yeah, it's an open problem actually to avoid this, because people are struggling with these kind of integrals where you don't have either a proper I epsilon or are not in the Euclidean regime, so where you really want to have an on-shell cut propagator.
Michi, could you
Yeah.
quickly comment on why you don't assume overall momentum conservation? So why you're leaving out one vertex? And maybe as a follow-up question, does then the integral depend on the vertex that you omitted?
No, the integral does not depend on the vertex that you omitted. You could also leave this V naught vertex in, and then you would just get a delta function. So this avoids an overall delta function, which just contains the sum over all incoming momentum into each vertex. So PV is the momentum that is flowing into a specific vertex, and if we add this extra vertex, then we have one delta function that just ensures that the sum of all these incoming momenta is 0. And it's irrelevant which vertex we omit. So to compute this incidence matrix, we need to fix.
Sorry, Michi, just to follow up. So this means that on the outer edges of the Feynman graph, you don't have momentum conservation, or do you? Because
we
this would-
assume it. We assume it. Yeah, actually, we need momentum conservation, but it's not really relevant for these integrals. It's just a
sure.
prefactor
Mhm.
that we are not writing down.
Okay, yeah, thanks.
Sorry, so here the integrals that you're describing only have denominators, right? It's like a
Yes.
scalar theory. Is it
Yes.
like to add like numerators? Do you have a standard way you do this? or-
Actually, you can also do numerators if you just put nu e to a negative number.
Okay, but that's a particular form of a numerator, right?
Yes, yes. Yes, you in more general cases you would also want to allow actual numerators where you are, so there's like something which is called, so many numerators can be dealt with by flipping around this nu, so making the nu e negative. But you're right that there are cases in this momentum representation where they are so-called irreducible scalar products, and you want to include them in the numerator, and they are not strictly included in this type of representation.
But what you're going to say after, would it generalize for the case where I would add some numerators in some way there?
What I'm going to say afterwards, so this derivation has to be augmented, but you could still do it. But also this is unfortunately not, there's no automatic way, at least I don't know an automatic way to include this into this parametric representation. And it would be fantastic to have one actually with this irreducible numerator.
Thank you.
But yeah, I don't know of any. So yeah, so if anybody likes this kind of derivation and wants to work out a way how to carry over numerators into this parametric representation, I think many people would be very happy and would have uses for this. So this is also an interesting thing to do. So yeah, so I want to be precise. So I'm going to give you a definition of this epsilon EV matrix. So you have to fix this orientation on the graph's edges. And I do this by example. So let's say the graph is this one here. It's a two-loop graph. And we have here these two external legs. So what does it mean to have an external leg in this notation? It just means that there's some non-zero momentum flowing onto this vertex. So in principle, we could also write P3 and P4 here, but we agree that because we didn't write a leg, this momentum that flows into this vertex P3 and P4 is just zero. So it's not squared zero, but it's 0, 0. And here we have some non-zero momentum inflowing. Now we fix an orientation, and we only fix an orientation on the internal edges, and it's completely arbitrary. And after we've done this, we can write down this incidence matrix. And it's just the matrix that we get if we write down plus minus 1, if so E indexes the edges of the graph and V the vertices of the graph. So this is an E times V matrix. And if this is plus minus 1, if this edge E points to or away from V. So depending on the rotation of the edge, we fix the sign. And if E is not connected to the vertex, then it's just 0. It is not incident to V. So this is the momentum representation with these delta functions in all its glory, without these irreducible numerators, unfortunately. And the disadvantage here is, like I already said, that we would like to allow for real value dimension. And we also would like to get rid of this delta function. And we also would like to reduce the dimensionality of these integrals a bit because the dimension is very high. And another problem comes from the fact that we are integrating over a non-bounded domain. So this is very bad for instance, numerical computer algorithms. So we always need something which is bounded and compact to be able to numerically integrate over it. And this is what we do by passing to the parametric representation. And this is what I'm going to explain now. So this also works in more generality. The problem then is that, yeah, mostly there are no combinatorial formulas then for the results, and I mean, there are no worked out combinatorial formulas. Probably they are, but you have to find it first. And to do this, we only need to know two integrals. So this is passing to parametric rep. So we need to know the integral for the gamma function. And this is this famous Schwinger trick. Probably have seen this before. So this is the defining equation for the gamma function. And we can just scale x by some arbitrary value a. So let's say this is equal from 0 to infinity x a nu times e to the power of minus ax. And the cool thing is that this works for all a with real part larger than 0. So in particular, we can just shovel around the a and the gamma and write these propagator terms up there as something which involves Gaussian, an exponential. And here you now see why the I epsilon is really important, because the I epsilon is exactly what guarantees you that you're allowed to do this trick here. And if you wouldn't have a definite I epsilon, then you cannot really use this formula anymore. cannot use this formula to translate these propagators into like something which is exponential. And this also tells you that, so you also have to use the epsilon if you have a non-Euclidean space-time signature, because in these cases, this A can change sign. So the real part has to have, thanks. The real part has to have a definite sign, and the real part in the Minkowski case is really only governed by this I epsilon. In the Euclidean case, you're in luck, because then you can just say this whole A here is just the Euclidean momentum, and it's positive anyway, so we don't need to worry about.
Sorry, there's a typo in the integral. It should be ax to the nu, not a to the nu. I just checked it with Mathematica.
Sorry, say again. What's
The second integral? It should be ax.
Ah, yeah. Here's a typo. Yes. Thanks. Sorry. That. Okay, so we can use that to get rid of these quotients, and yeah, this is the other thing that we need to get rid of are these delta functions. So there's a different integral. Oh, no, wrong one.
Yeah, sorry. Does the prescription of the I epsilon matters here? But because it seems like for the sake of convergence, it doesn't matter for the sake of convergence. Sorry here.
Yes, it matters for the convergence. Or
yes, but the prescription, like the Feynman or retard or advanced, this doesn't matter at this stage. Is that correct?
I don't understand. So what's the question again?
Yeah, the prescription of the I epsilon, does it matter to define the integral?
No, I mean, you can write down integrals with all kinds of I epsilons and the prescription and solutions of the propagator equation. But the problem is that you cannot use this trick here, the stringer trick, in case you don't have a I epsilon. So this is the whole statement.
Okay, I see. Thanks.
Yeah, and before go into the break, and maybe I can still finish this. So there's a Fourier integral representation of the delta function.
Sorry.
Yes.
Here in the shouldn't there be like an x in the exponent in the integrand and a 1 over gamma?
Yes. I'm sorry, it's another typo. Yes.
Okay.
Thank you. Yes, good. Thanks for paying attention. Very well. So here we have the Fourier representation that also involves an exponential. So we are integrating over d-dimensional space, and we are integrating now over all, say, positions y, and the integral is just the Fourier representation, or the exponential of the dot product of y and k, and it's also a kind of very oscillating integral. And so we can use these two integral representations of the various terms to write everything in this Feynman integral in terms of an exponential. And this is the last step that I can still do before the break, maybe. So we apply these kind of formulas just to the expression above. And what we get is this almost parametric Feynman integral. So we have a product over the edges and an integral for each edge. And then we substitute this Schwinger trick one for each edge. And we have another product for all the vertices, or vertices minus 1. And here we do the other integral representation, this Fourier transformation of the delta function. And I hope the factors of pi are correct. And then the actual integrand is just an exponential integral. And it involves the sum over the edges that comes from the propagators. And the sum over the vertices minus 1. With this epsilon matrix. And what you see, of course, is that now the integrand is a nice Gaussian in these Q's, and it's linear in the Y's, so it looks linear. But if we complete the square in Q, because we also have a linear term here in Q, you can imagine that we also pick up a square term in Y. So what we have here is like a double Gaussian integral over these Q's and these Y's. And these are the annoying integrals because they both involve d-dimensional space. And if we perform this Gaussian integral, then we are left over with only this integration over these Schwinger parameters x, and we derive the parametric representation. And you see that this, I mean, it's constrained by this I epsilons, but it also works for cases where we actually have linear propagators. So this is also interesting for gravitational wave computations, for instance. And what's also an interesting problem is to work out the details of this approach if we have like specific propagators made linear, and then work out the structure of these matrices that pop up if we have like, if we set like some if we put some linear propagators in. The numerators are a different problem, which is also very interesting. Yeah, I think it's a good time to have a break now.